start. Okay, may I start? Sure. Yeah. Okay, so my name is Gianni Amisano. I work at the Federal Reserve Board, and I'm very grateful to have been included in the program. So this is a conjoint work with Oreste Tristani, who's at the ECB, and of course the usual disclaimer applies. Okay, so one thing that I wanted to say is that this is really very preliminary work. It's the first time that we present the results on some of the results on this project. So, so what do we do here? So the motivation of the problem is that of this work is that you know that we focused on the natural rate of interest, which is the real short-term interest rate, which is consistent with stable inflation and in the absence of inflationary pressures. And this is obviously a very useful benchmark for the monetary policy stance. So the monetary policy stance is defined as being expansionary if the short-term real interest rate is below the natural rate, and vice versa. So it's basically, you can think about like, you know, it's kind of like the polar star for monetary policy. And you know, one thing is that, you know, we can think about that rate to be such that at any point in time there is a full term structure of current and expected future natural rates, which really basically gives you the path that the monetary policy authority should follow in order to you know, control inflation and you know, basically stabilized. So our objective in the paper is to provide an empirical estimate of the term structure of natural rates of interest using a structural model. Okay. In our approach, what we do, we combine macroeconomic data and information from bond yields in a unified structural framework. So we have both macro data and term structure data. So we know that by previous work, in particular Christensen and Rudebusch, that bond market information is valuable to, you know, basically to make inference on the natural rate. And after accounting for the premium, bond yields provide, in fact, direct evidence on expected future real rates. And you know, what they find also is that far ahead future horizons, real interest rates are tied to and thus provide information to the natural rate. In our approach, we need a structural framework to operationalize the notion of the natural rate, so to ensure that it does represent indeed a useful indicator of the monetary policy stance. And for this reason, we define a natural rate as the real interest rate that will be observed in a counterfactual world without nominal rigidities and inefficient cost push shocks, following Woodford's. So basically, we take the natural rate, the notion of the natural rates that is defined in DSG models. So we know that in this case, the real natural rate is independent of monetary policy, and if it's tracked by monetary policy, as I said, it ensures the absence of inflationary pressures in the face of all, but not cost push shocks. Okay, so this is a preview of our results, and again, you know, these are very preliminary and might change in the you know, in the details. So if we impose model consistent, no arbitrary restrictions of bond actual and natural yields, we get natural rate estimates that have a plausible level of high frequency volatility. And this is quite interesting because usually the natural concepts in DSG models, like the natural rate, or also, you know, basically the natural unemployment rate, or the potential output, you know, the natural rate of output, and so on and so forth, tend to be very volatile. Okay, so we don't get that. We get something which is not really volatile, and you know, you know, basically this is an intuition of these results. You know, and having not much volatility is a good thing, right? And the reason why we get this result is that while volatility plays no role in linearized models, in our model it does, because we solve the DSG models to second order approximation. In that way, you know, basically volatility have effect on conditional expectations, and so volatility is by de facto is in a sense it has a role which is limited. because if the model is solving by linear to linear approximation, the volatility would not have impact on the levels of the variables, and therefore the model would be the estimation strategy would be free to pick even kind of a not reasonable levels of volatility. Okay, so whereas now we have a situation in which volatility directly feeds back to the conditional first order moments of the variables, so on the level of the variables. In a mechanism which is quite similar to a Garchin mean, like the mechanism that Fabio was describing this morning. The only difference is that this mechanism is structural, so it's basically related to the solution of the model. Okay. Regarding policy, our results show that real rates have been quite consistent with the natural rate over the most, the last 35 years, and this is something that might, be kind of a pleasant result for the Federal Reserve, for my institution, because it means that we have been basically doing quite a good job. So this is a sign that the Federal Reserve stabilizes appropriately all shocks which do not produce a trade-off between inflation and the output gap. And also regarding the long-run natural rate, our estimates are consistent with the existing results in the literature. We basically show that, the natural rate has been kind of gently trending downwards in recent years. Okay, so the related literature. Okay, there is a long tradition of estimating natural rate of interest in the macroeconomic literature, a paper by Edge and co-authors, Giustiniano e Primiceri, Barsky, Giustiniano Melosi, Cordia and co-authors, and so on and so forth. And this literature has, in a sense, has ignored the financial market information, whereas, the paper by Del Negro et al. in 2017 has kind of incorporated analysis of the natural rate. It has incorporated using a medium-scale DSG model that uses some financial market information estimation. But it basically relies on the expectational hypothesis for the term structure. It doesn't do anything on that front. Whereas what we do is we model term premia endogenously and impose no arbitrary restriction. So you basically have a structural way to model the term structure, which is based on an arbitrage conditions that obtain from considering the model implied the stochastic discount factor. Okay, so, and we find that this is particularly useful to inform the natural rate estimates, okay. There is another strand of the literature which is less structural, and this basically started with the work by Thomas Laubach and John Williams with the definition of the natural rate as R star. As the real short-term interest rate, which is consistent with output equaling its natural rate and constant inflation. And there have been a lot of different papers on this, basically more on a statistical measure of the natural rate. I quote the literature here. There's the paper that Christensen and Rudebusch, in which they estimate, they define the R star as the investor's expectation of the real short rate for 5-year period starting 5 years ahead, and also a recent work by my co-authors Gonzalez and Lafort at the board, where they use a semi-structural model to jointly estimate R star, the natural rate of interest, and the output gap, all simultaneous in a semi-structural model. Okay, so what do we do? So what we did, is basically the following. So we took the model that we estimated in a paper published last year on QE, and this paper is basically has a DSG model with 2 distinguishing features. So we have an unexpected utility preferences, which is useful in pricing risky assets. And the other feature is we have heteroscedasticity, so in the form of regime switching, hence the relevance the paper for this conference. So we have Markov switching in the variances of some shocks. The 2 things together give us a very good way to model and to obtain time-varying risk premia, which are meaningful in a structural way. And we use macro and yield data, so we use data on, say, GDP and consumption and the short-term interest rate and inflation and so on and so forth. Plus, we use data on different points on the term structure to inform estimation, okay? That's basically what we do. And so we took that model and we basically said, well, why don't we just try to back out from this model the measures of the natural rate? So, it's basically, the paper is just the textbook example of a spin-off paper, right? You use something that you have and you see how it works for doing different things, okay? So sometimes it works, sometimes it doesn't, all right? The preliminary evidence that we have, it seems that it does quite, okay. So we did re-estimate the model in different subperiods and so on and so forth, but for the results that I present this evening, I'm going to just stick to the estimation which is closest to the one that we had in the paper. So, from the mid-1960s to the end of 2019. And as you see, we're basically trying to give the COVID years a wide berth because, it's particularly problematic. Okay. All right, so the model fits the data well, and the estimated parameters are quite consistent with previous studies. You can see on the QE paper details on the parameters estimate. And what we did was basically, as an external validation device, we compute the model-based real yields that the model generates, and we compare them to the existing data on index-linked bonds, which are basically what we call TIPS, which are available for the US, which we didn't use for estimation, and that we can use basically as a sanity check on the model. Okay, right. So the first ingredient of the model is the regime switching. So there are some shocks in the model, in particular productivity, which we call Z, and eta, which is the monetary policy shock, which have variances which oscillates between two possible values, a low value and a high value. Okay? And each of these two regimes for these two different shocks are basically micro-switching and are independent of each other. Okay? We find it quite interesting because, monetary policy has been kind of adhering to, let's say, the Taylor principle, loosely speaking, with different degrees of intensity, and, having, a volatility that of the error term of the monetary policy shock that can be allowed to vary is useful. And the other thing is that we can think about the changes in volatility in technology is something that is akin to some sort of like uncertainty shock, which, we show that in the model has quite a big importance, both on the real variables, but also on the dynamics of the term premia that come out of the model. Okay, so that's it. And so when we estimate the model for a longer period, let's say from 1966 to 2019, we need also, it's not really strictly necessary, but we did it for the QE paper because it was asked by the editor, so we did it. We were not really enthusiastic about that, but we did it. So we also introduced a target. Pi star T is basically the target for inflation in the Taylor rule, and also we have basically a micro-switching process for that. Okay, so we can think about like something that let's say before the end of the 1980s was higher, and now it's lower. Okay. And this complicates things a lot, as Junior and other people know, because this micro-switching process is the parameters of this micro-switching process will enter in the non-stochastic steady state. And this is going to be complicating the solution strategy quite a bit. Okay, whereas if you have only the variances shifting, they don't enter in the non-stochastic steady state because they are part of the stochastic mechanism, not the non-stochastic mechanism. Okay, so that's basically the idea. The second element in the paper is this non-expected utility. So people, might be familiar with this or might not. So we have this Epstein and Zinn kind of preferences, in which we basically distinguish between the parameter that gives the inverse of the elasticity of intertemporal substitution and the risk aversion. Okay, so typically in constant relative risk aversion specification, the two parameters are basically the same. Here there are two different parameters, and this is a trick which is very much used in applied asset pricing literature, and it works quite well and has been used a lot in DSG models. Okay, and so this is the form of the utility function. The utility function, the instantaneous utility function, is basically people like consumption, people like consuming, but dislike working, and there is some habit persistence in the utility function. Okay. Okay. So we also have other shocks. We have a markup shock, which is a non-efficient shock in this kind of a framework because it creates some trade-off between the output gap and inflation. Then we have a demand shock, which we call G, such that output is equal to consumption plus this demand shock. And we have a technology shock that has both a permanent and a transitory component, and it's the transitory component that has a shock that is Markov switching, okay? And all these shocks have AR1 processes. Okay. Okay. So we have then a Taylor rule. This is basically just a very traditional Taylor rule with there is a target that, as I said, is it's Markov switching in the longer sample. And it's really pretty standard. There is a monetary policy shock which variances is also Markov switching, okay? Then, going to the meat of the paper, so the natural rate of interest is basically, closely related to the expected value of the real stochastic discount factor that comes from the model, okay? So basically it comes straight from the ratio between the marginal utilities in consecutive periods in the model. Okay, so that's the way in which the natural rate is backed out from the model. How much time do I have?
I think you have about 10 minutes.
10 minutes. That's good. Yeah, I'm doing quite well. Okay, so the solution. Here I will go very fast, even if I suspect that many kind of a Markov switching, especially Markov switching DSG enthusiasts would want me to talk more about this. But so we solve the model to second order, and we use a solution, basically a solution, which a perturbation-based solution that we describe in two papers. So the solution generates for the state variables x's and for the control variables y's, basically two sets of quadratic equations. Okay. And so the quadratic equations are such that there is an intercept, and the intercepts are the only thing which are affected by the Markov switching. Okay, so the Markov switching to first order would not basically affect the linear terms of the solution. If you go quadratic, we show that the quadratic terms as well are not affected by Markov switching, but the intercept are. Okay? So this is quite cool because one can think, hey, going back to what Fabio was saying this morning, so we have a mechanism in which we have a feedback from volatility to the levels, right? And this is not ad hoc. It's not something that is postulated. It basically comes out of the structure of the model, okay, which is cool. Okay, so the complication, so the solution is quite easy. It's not very expensive computationally or even conceptually. It's expensive in terms of being put to estimation. Okay, so this is a state space model with Markov switching and with a quadratic structure. So we cannot do Kalman filtering here. Okay, so what do? So we spent a lot of time trying to do particle filtering, but it wouldn't work very well. So in the end, we resorted to using an approximation of the Kalman filter that works quite well. Okay, so we use basically the extended Kalman filter. And it works quite well. The details are in the QE paper. Okay, so I've already talked about that. And so, we can come to quite an inexpensive way to compute the likelihood, and therefore we can stick it into an MCMC Metropolis algorithm that works quite well. Okay, so It works quite well, but in order to obtain a simulation that a simulation size which is useful, you need to run the model for 2-3 days. Okay, so quite well. It's not. I would prefer like 2-3 hours, but instead it's 2-3 days. Okay. Okay, so first of all, what we do is basically to take the results of the estimation and to, as I said, the model produces a lot of unobservable variables. So you can compute the forward rates, you can produce swaps, you can produce index link, so real rates, so you can compare them with the data. Okay, so that's the first kind of a sanity check that we perform. And, so both, in this figure you have two, basically here you have the yields on, 3 months, and, 3 years and 10 years. For the longer sample, 66 and 2019, and for the shorter samples that we estimate 87 and 19. And the blue line, and the yellow lines are basically filtered, and the yellow and the red are smoothed and filtered from the model, and blue is the data. Again, I want to emphasize the data are not used for estimation. Okay, the data on the real yields, and as you can see visually, they're pretty close. Close, but not perfectly close. So in effect, here we have sort of like a fork in the road. One way would be to take the model and augment the observables with this data, and then of course the fit would improve in that dimension, but then we would have to resort to any kind of other kind of external sanity check for the model itself. All right, so that's basically the thing. Then if you want to to go and see the natural rate in the short run, so we have the basically we can back out the natural rate from the model. Also we compare it with the model real rate, the model generated real rate. And the nominal 3-month rate is estimated as a shadow rate over the period in which the actual short-term rates were constrained by the zero hour bound. So in that period, we basically substitute missing values. So that's basically what we do, and this is basically the picture, the main picture of the results. So the blue line is the natural rate, and the red line is basically the real rate that comes out of the model. So we can see basically a few things here. So the natural rate is highly cyclical, increases during expansion, and then starts falling at the beginning of each recessions. They are quite close, natural rate and the real rate. They are persistently different just at the end of the sample after 2017. Remember here the sample finishes in 2019 Q4. There, after 2017, the natural rate keeps increasing towards a 2% level, while the real rates tend to hover around 0. And the rise in the natural rate is a signal that the model sees positive aggregate inflation pressures, and one can think about this as kind of irrelevant in a situation in which it was forward guidance. So, kind of a pretty interpretable. And all in all, the model interprets monetary policy as consistent with the aim of offsetting all efficient shocks. So all those shocks that do not produce a trade-off between inflation and output gap. And, the model is not particularly volatile at high frequencies. And, the reason why that happens is that, the volatility has an effect on the conditional means. So it cannot go unreasonably high. Okay, at longer horizons, we can back out basically the expectation for the natural rate at different horizons, and so we find that that basically comparing with other approaches in the literature, Laubach and Williams, Olson, Laubach and Williams, Lubick and Mattes, we find out that our result find that this kind of expectations of the natural rate on over long horizons are consistent with the idea of a progressive fall in R star over the estimation sample. Okay, is more abrupt at the 5-year horizon, while it's smoother at the 10-year horizon. Here, a little bit of taste of these results. So this is the 1 year ahead, this is the 3 year ahead, and this is the 5 year ahead. Again, the blue is the natural rate, and the red is the real rate. So you can basically see a little. If you squint, you can see the downward slope. So recap what we found. Do I still have 1 minute? Great. So recap. We present empirical estimates of the term structure of natural rates based off a unified structural framework, which is a DSG, combining macroeconomic data information from bond yields. We use the DSG notion of the natural rate. Our estimates show contain high frequency, show kind of a limited high frequency volatility in the natural rate, and we know that this depends on the fact of this kind of a nonlinear solution. The results suggest that real rates have been quite consistent with the natural rate over the periods that we take into consideration, not only the, basically also the longer period, not only 87 2019. We have a very simple structural model. We could think about having more features being brought to the model itself. In particular, we're really not totally sold with the way in which we deal with the zero lower bound. We did something which was a little bit expedient. Just using this kind of a notion of shadow rate by making the short-term real rates, the short-term nominal rate not observable. Okay, so that's what we have so far, and we hope to get in better shape in the near future. Thank you for your attention.
Thank you so much. Thank you so much. You are really on time. So let's open the floor for questions. Any questions? Comments? Junior?
Thank you so much, Gianni. This was really, really nice. But then it would have been natural for you to compare with the expectations hypothesis to see that there are differences. Perhaps you should show a picture like that as well. Yes, so also you do a second order approximation. I'm wondering if you did a first order approximation, could you also compare that to show that, so that we can clearly see the benefits of the second order?
These are excellent ideas, and we'll do that. Especially the first one, I like it a lot because what you do there, if you just use the expectation hypothesis, you will basically have the term structure of the natural rate without any allowance for risk premium, okay, or term premium. And that's really useful to compare that with the literature, which instead uses just like statistical notions of the R star. So in fact, one of the aim of the paper, I haven't written it down, is basically also to assess which is the relevance of the premium on the term structure of the natural rate. Of course, the premium are really relevant for the actual term structure of the actual rates, but we don't really know for the natural rate. Okay. At first sight, it doesn't seem that much important because the real rates in the long run, the real rates and the natural rates, the expectations are pretty close. But that's an exercise which is really important. And of course, yeah, always comparing to linear model is always a very good idea, and we'll do that. Thank you.
Thanks for the very interesting presentation. Was there any reason why you avoided using the shadow rate as a sort of quick and dirty way of doing the estimation? You just left the short-term rate unobserved, you said.
Yeah.
Did you, okay, that's one. And then just maybe a more, just your view here. When we extend a model like this to include some sort of financial frictions, what is your view on the finance neutral, so like the flex price equilibrium, or, which is what's normal? What is your view of the finance neutral? So would you, if you wanted to think about the natural rate in this environment, would you just remove the nominal rigidities and keep financial frictions and say this is the natural rate, or would you want to remove both? Yeah.
Okay. Yeah, so very interesting question. So the first one, in a sense, one person would like to have, to treat the zero lower bound in a different way, and there are ways to do it. So you introduce a further source of nonlinearity in the model, that can be handled in different ways. Guerrier and Yakovleva, or other things, other ways. So we decided this because we thought it was the simplest to just try and get some results out without having to spend too much time. But it's certainly, as I said, something that we will reconsider. Okay.
So you don't have a problem with the shadow?
No, I don't. I don't have a problem. Yeah, yeah. I don't have a problem, but I just thought that it was too good to be true that we could just deal with that problem with not availables. Just opening your Excel file with the data and just cancel some numbers. That seems too good to be true to me, but this is just like my intuition talking, not kind of a rigid analytical argument. Regarding the cost of natural rate, when you have a bunch of shocks, like, for instance, financial frictions and so on and so forth. I mean, I have to say, I really would like to have some financial frictions, because I think that, when you model risk premium, you obviously want to, model, basically agents' attitude to, relevant sources of shocks, right? So I really would like to have a model with financial frictions, but then I would be in your predicament. The binding would be, what do I do with the shock? And basically then you have a multiplication of concept of natural rates that depend on which shocks you bring in and which shocks you bring out. The advantage of this model is that basically we have just to zero out the cost push shocks. We have just one, and that's it. And again, I'm not saying this is good. I'm just saying this is simple. Yeah. But maybe the concept that we have to follow is that expunge all the shocks which are not really which are basically not efficient.
One small question: can you, with this model paper, discuss the issues of good luck versus good policy? Because I mean, you arrived to the conclusion that it's good policy. Why is not good luck?
Well, the point is that, here you can think about that good luck is basically what happens to the balance of the shocks, at least the technology shock, and whereas a good policy is the way in which you have variations in the inflation target. And if we look at the variance decomposition that we can back out from the model, it turns out that the variables, the observable variables in the model are more influenced by the changes in the volatility of the technology shock. So in the paper, we didn't really take a strong side on that debate, but just looking at the variance decomposition, I would say it was more good luck than good policy. Yeah.
I guess we are running out of time, so let's thank Gianni. Thank you so much.
So thank you, Gianni. We do have a couple online questions, and seeing that we are still streaming, it's both from the same person, and it's leading on from Junior's topic of the natural interest rate. This gentleman asks, he says, what is it? It is very sensitive to definition details, including parameters like uncertainty. Why do you need it? Monetary policy shocks already show how tight policy is. And then he has a comment saying, extended Kalman filter is not accurate. Sigma point or Gaussian assumed Kalman filters are much more accurate with almost the same computational costs. So that's just some comments. Thank you.
So, the natural rate, as I said in the discussion we had before regarding the definition of natural rate, I'm very uncomfortable myself on the definition of the natural rate. But that's basically what we get out of this model. We can define it in the way we did, in a way which is kind of uncontroversial here. Again, I know that in more sophisticated models and maybe more realistic models, is less, is kind of a more controversial. And if you hear kind of a central bankers talk, in their public speeches and so on and so forth, they always refer to kind of a notions of, when you think about how restrictive monetary policy is and why not, that's kind of something that, it's useful to measure by using the gauge of the natural rate. So it's basically just like, a navigation device, okay? And then the other fact about, which filter to use, I'm totally open to use other ones. We know that it's inaccurate, even if I have to say that in the QE paper we have a some, I can't remember whether it's in the paper or in the online apprentice, but we were asked to show the accuracy of the method we used, and it was, quite acceptable. But I am, if I can get advice on using other stuff which is more precise and as at least not more kind of numerically involved and time consuming, I'm very happy to take all this recommendation. Thank you.
Thank you so much.
Thank you.
Oh, one more?
Break time also. Yeah, break. As many questions as we want. No, Gianni, this was very good. You said something earlier about the fact that the steady state was shifting.
Mm-hmm.
Yeah, and
Yeah.
But you didn't say anything about how you handle that. Also, because you do Markov switching, it would be natural to present the regime probabilities.
Oh, yeah, we have them in the paper.
Yeah.
So, I'm starting from the last thing because it's easier to answer to. So, we have these, these marginal regime probabilities in the paper, and they make sense.
Mm-hmm.
They're basically, you have high volatility for the monetary policy shock in the Volcker during the Volcker monetarist experiment, so it's all good, and you have very nice cyclical variation in the volatility of technology shocks, which basically are in sync with the business cycle phases and so on and so forth. So that's, and also, the dynamics for the probability of pi star are quite sensible. Okay, so we have them. We have. Regarding the first thing that you mentioned. So again, if so you are an expert in this, but just talking to the rest of the crowd. So if you have Markov switching mechanisms, and the mechanism affects the non-stochastic steady state, things become really very difficult to get the solution. And there's this paper, I think it's on QE, by Wagner, Ja and Forster, and so they explain what to do there. So if you don't have the shift in pi star, things are easy. Okay, when you do have shifts in pi star, things become a little bit messier, and there is a paper by Liu and Ja that do. Basically, they suggest a way to get to the solution there. And in the end, we did that in the QE paper because Tao was the editor, and he suggested that we use his paper, and we did, and we got the paper published.
Yes, no, but all of those methods are implemented in RISE, and for RISE, it's not a problem.
Oh yeah, that's good.
Those things that scare you are not a problem in RISE.
And what do you do for estimation? Oh, but it's linear models.
No? I was wondering why you stopped at second order. You could have done fifth order if you had used RISE.
Yeah, no, the point is that we try to do third order, but the terms become so kind of small that the cost-benefit analysis of basically getting tensor matrices that are so high in a situation in which those terms are so small, it became to us.
Yes.
Yeah, a little bit kind of we thought it was whimsical to go higher order. And, so we basically stuck the simplest approximation that would deliver us time-varying non-zero premium.
Time-varying non-zero? Premium.
Yeah. But I will check RISE. I haven't really been attentive to that. I've been rationally inattentive to that.
Thank you so much. Let's close the session.
Thank you to the chair.
Thank you. Thanks so much. Sorry to have dropped them before.